All right, welcome to Real Engineering Mechanics, as I would call it, or the problems that really make my heart sing, and probably the heart of every structural engineer. What you see from now on are probably the topics that either make you fall in love with structural engineering or hate it. But of course, I'm a structural engineer, so I love it, and I think it's really fun to determine the equilibrium of these force systems. So here we are asked to calculate the support reaction for the steel beam that has three loads on it, 20 pounds, 30 pounds, and 40 pounds, and then has, of course, given distances for each of these forces. And the first thing we always have to do when we see these problems is to draw the free body diagram before we can actually solve it. And what I do to help myself with this is usually I kind of bring down the dimensions. So let's do that first. And here we go. My next force and the end of the beam. And then I have to draw my free body diagram. And remember what we talked about, that the free body diagram is now representing a rigid body, and a rigid body always has a dashed line to identify it. You will learn more about this later, but for now just apply a dashed line on the bottom. Sometimes you can put it on the top later on, but for now just put it on the bottom. All right, now we have to look at the symbols here, or the representation in the picture. This here could either be a pin, a rocker, or a fixed support, and this one here as well. But the symbol or the image gives away what it really is. This one here allows the beam to slide on top of it, so therefore it's clearly a roller or a rocker. Whereas this one here has the pin actually in there, and it prevents horizontal motion, vertical motion, so therefore this would be the pin. In other words, we actually have to represent the forces in our free body diagram now. So obviously I need a force that is acting in the vertical direction. I call that RAY. But because it's a pin, right, I also have to add a force in the horizontal direction, and I call that RAX. And then because we have a roller on the right side, I only have one support reaction, which then is RBY. And for my free body diagram to be complete, I need to add my forces. So I add those. And of course, I properly identify them. And now I'm done with my free body diagram. Now I can go ahead and solve this problem based on my free body diagram. And what I do is I want to find RAY, I want to find RBY, and I want to find RAX. And RAX would be calculated as the sum of the forces in the x direction being equal to 0, and 0 is equal to plus RAX, and therefore it's equal to 0. That is already an answer. But please note that I still calculate it. I still calculate RAX to be equal to 0. It's a result. All right, let's find RAY. Remember from our explanation before that if I want to find RAY, I need to make RBY disappear. So I take the sum of the moments about this point. So I write down the sum of the moments about B is equal to 0, counterclockwise positive. And then I say 0 is equal to RAY multiplied by, I need to bring down my lengths here. So let's actually do that. So we have 3 feet here, 6 feet here, 2 feet, and 1 foot. And now I can use those dimensions to calculate my lever arms. So the entire structure is 12 feet long, if I'm not mistaken. Therefore, my RAY has a 12-foot lever arm. And now the question is, does RAY turn clockwise or counterclockwise about this point? It turns clockwise, therefore it's negative. And now I have to deal with all my other forces. So let's start with the 20. So 20 pounds multiplied by What distance do I have here? So from here to here I have 6, 8, 9 feet. So times 9 feet. The question is that positive or negative? And the answer is positive because it turns counterclockwise. Then I have my 30 pounds multiplied by, what's that distance now? From 30 to B, right? So which is here, that would be 3 feet. So I multiply that by 3 feet. And that is also counterclockwise, therefore it's positive. Last but not least, I have 40 pounds, which is no secret at this point, is also positive, and that has a lever arm of 1 foot. And now I can solve the equation. I can just state that RAY is equal to 20 times 9 plus 30 times 3 plus 40 times 1, and the whole thing divided by the entire lever arm, 12. And please notice the physics of the entire equation, right? So I have pound times force, pound times force, pound times force, and that needs to be true for all of them. So it's a moment equation, which is indicated here. But now I take moments and divide them by 12 feet, right? So just to be clear here, what we have is we have something that is pound foot divided by foot, which then of course returns foot, which is good, returns pound, which is good because we obviously want to find a support reaction in pound. And if I calculate this out, I will find that my answer is really 25.83 pounds. And that qualifies as a result, so I double underline that and use my answer arrow. And I have my first result. Let's do the same thing for the other equation, for RBY. So to calculate RBY, I take the sum of the moments about A to be 0, counterclockwise positive, and then 0 is equal to plus RBY multiplied by 12 feet. And now minus, let's start from the left again, minus 20 pounds multiplied by 3 feet minus 30 pounds. And just for those who are puzzled, let's just write it as 3 plus 6 feet. And last but not least, minus 40 pounds multiplied by 12 minus 1, if you will, or 3 plus 6 plus 2, which is really 11 feet, right? And so I can now rearrange that equation as well. And so I can find that RBY is equal to 20 times 3 plus 30 times 9 plus 40 times 11, and this whole thing as well divided by 12. And if I calculate that out, I will find that RBY is equal to 64.16 pounds. And that once again is a result that I have to not just double underline, but I also have to verify it. And I want to talk more about the verification in a second. So now I can use my force equilibrium to really verify this result and to actually be sure before I turn in my exam or my quiz that I'm correct, right? So I can say that the sum of the forces in the y direction is equal to 0, and 0 is equal to plus RAY plus RBY minus 20 minus 30 and minus 40. And what you will find is that this here is equal to 90 or negative 90, and that these here are equal to plus 90, and therefore I can check it off. And I am certain that I didn't tell you anything wrong here. I actually found my correct results. Let's talk about this for a second again. So please understand that you always have to report 3 results for these support reaction problems, right? So you always have to provide RAY, RBY, and RX in this case. Of course, this might be different. So for example, you can have the pin on the other side, you can have the roller somewhere else. So the letters might change or the arrangement might change. But for us in this class, for now, you always have to report 3 results. We will learn more about this in future lectures, but it is a given in this class that you always have 3 support reactions. Otherwise, the system would not work for reasons we do not understand yet, but believe me that the system would not work if you don't find 3 support reactions, even if the support reaction ends up to be 0. And so one thing we want from you here is that you can identify where the horizontal support reaction is. So for example, if you would have placed the horizontal support reaction here, which sometimes I find students do in an exam, that is of course not correct, because here you have the roller and not the pin, and therefore you would lose points. So please understand that, and also understand how the equilibrium moment equations work as they are exemplified here. And then last but not least, understand that we have a moment divided by a lever arm, and that turns it back into a force. And I believe that completes this example, and we are ready for our next one. So here we can see our next example problem for a simply supported beam with, in this case, 2 forces on it, and you are supposed to find the support reaction at A and B. Notice that this is already given in symbolization form. So here you have clearly the pin because there's no sliding surface, and here you have clearly the rocker or roller because the roller is having the sliding plane right here. So that means that the horizontal force would be resisted at A, whereas vertical forces are resisted at B and A. And notice that the force on here are not just vertical, they're also horizontal. So there is a force component that acts in the horizontal direction that must be resisted at A. And I think that allows us now to draw the free body diagram. So let's go ahead and do that. And of course, again, this is a free body diagram. Therefore, I need to use my dashed line because it is a rigid body. And I have support reactions RAY, in this case RAX. And by the way, it doesn't matter in which direction you assume RAX or RAY, because notice that here I'm just assuming. I mean, intuitively, all of us know that the force is going up here, but you don't know if RAX is going to the right or to the left unless you have some experience. But what I'm trying to tell you is it doesn't matter. You could even assume RBX to go downwards in this case. But that would just make you find a negative answer for RBX. All right, now I have forces acting on there. So I have 10 Newton in this direction. And I have actually my life easier if I break it down into a vertical and a horizontal component. So let's call this here 50 Newton times sine of 30. And then I also have a horizontal component, which is equal to 50 cosine of 30. And now we can write out the equilibrium equations for this system. Let's go ahead and do that. So first, let's find RAY. It's the sum of the moments about B being equal to 0, counterclockwise positive. And therefore 0 is equal to minus RAY, negative, right? Minus RAY multiplied by the lever arm, which happens to be 4 plus 1 plus 2, so that's 7 meters. And then minus 10 Newton. And the lever arm now is 3 meters times 3 meters. And minus, be careful, because it's only the vertical component that creates a force. So I need to take this entire system here, right? So the 50 Newton. So in fact, I color code this just this last time. 50 Newton multiplied by sine 30. And then that needs to be multiplied by the lever arm, which relative to B is equal to 2 meters. All right. Okay. So now you could calculate that out. I don't even have to do that right now. So RAY is equal to something. Just conceptually, I'm going to show you how to find RBY, which is the sum of the moments about point A being equal to 0, counterclockwise positive, and 0 is equal to plus RBY times 7 meters. So that's the entire distance between RBY and the support A. But I actually already made a mistake here, so let me fix that. It's not positive in this case. It's actually negative because I assumed my force to go clockwise about this point, right? So I assumed it downwards, remember? It doesn't matter how you assume it, you just have to be truthful in your equation, and I wasn't here, so I need to actually make this negative because it turns clockwise. So negative, and if you wanted to put in parentheses to understand it's a rotation, then that is fine. And now I can use my other two forces. Let's start from the left. So minus 10 Newton multiplied by 4 meters, because I'm turning about A, and minus 50 Newton multiplied by sine 30 multiplied by 5 meters. And you can calculate what that comes out to be, RBY. And then, of course, don't forget to check these, right? So you would run a check. And the check would be the sum of the forces in the y direction being equal to 0. And 0 would be equal to plus RAY minus 10 Newton minus 50 Newton times sine 30. And then be careful, now it's minus RBX. But what you will find if you solve this is that RBY actually, so let me fix that. RBY here. So what you will find is that RBY is actually negative. So that force will be minus something, and of course in Newton. And this one here will come out to be positive something in Newton. But because you found that this is a negative answer, you have to plug in a negative here as well. And then negative and negative gives plus. Because in reality, this support reaction will push up. And you cannot change physics, right? In fact, that's something you need to always keep in mind when you solve these problems. You always need to think about the physics behind it. And it is so easy to check your results, for example, using this equation, and to make sure that your physics checks out. So please do that and understand that if you were, for example, to plug in a positive number here and then you subtract it, that this equation cannot be 0 unless you made a mistake in your calculation. All right, so we have two results so far. Let me actually double underline them. We have this result and we have this result down here. But we need a third one. Remember, we always need 3 support reactions, and in fact we need RAX. And so to do that one, I do the sum of the forces in the x direction being equal to 0. And 0 is equal to my assumed RAX, so plus, and I sometimes use a double plus, so plus RAX. And let me explain that to you. So this one here says that my RAX is positive in the sketch sense, right? So I sketched it positive, but it's also positive in my directional sense, which I did not indicate here. So now I indicated it. So this positive comes from here, whereas this positive comes from the sketch. And that sometimes helps me to check myself. And now what acts against that is the minus 50 Newton times the cosine of 30, right? And so you can now solve this equation and find that RAX is really equal to positive in this case because they are actually acting against each other. This pushes to the left, this pushes to the right. So I find a positive result for this one because they have to be in balance. And therefore I find that my answer here, without really calculating it myself, is plus 50 cosine 30. And that is a result as well. And therefore I now have my 3 results and my 3 answer arrows that I need to indicate that I solved the problem. And therefore we now completed our entire problem here, for which we were supposed to find the support reaction. I leave the numerical values up to you. Of course, you're more than capable of finding the right answers here and conceptually thinking through it. But this completes this example, and we are now ready to move on to more complicated examples. So here we have our next fun example, which usually causes confusion in the classroom simply for the fact that we now have a support reaction that sits in the middle under the beam. And please notice this half circle. It's not a full circle that would actually turn this into a hinge, and therefore this part of the system would be unstable if there was a hinge here. So there's only a support underneath it and not in the beam. So we have the pin here on the left side, we have the roller or slider on the right side, and we have an overhang here, which makes the problem interesting because now you have to be careful in which direction it rotates. But let's take a look at it and draw the free body diagram real quick. So the free body diagram would look as follows. Of course, my rigid body must have a dashed line. And I need to indicate that I have my roller on the right side in this case. So this here would be RBY, and it has no other support reaction. RAX right here and RAY right here. Now let's take care of the forces. So I have the 20 Newton acting right here. And then once again I have 2 force components. One is going down and the other one I might as well draw here. It points to the right and it points down. So here we have 100 times sine 70. And here we have 100 times cosine of 70. And now I can use those to calculate my support reactions. Let's go ahead and do that. So I start in this case with the easiest one, which is RAX. So to find RAX, I use the sum of the forces in the x direction being equal to 0, positive to the right. And 0 is equal to plus positive RAX plus what's positive actually as well is 100 cosine 70. And so what you will find is that you actually now have to invert RAX. So you find a negative RAX. Or even better, you will find that RAX is equal to minus 100 cosine 70. And that comes out to be negative 34.2, in this case, Newton. And it's very important to understand what the negative means, right? The negative does not mean that my arrow is pointing in the negative x direction. It's very tempting to think that, especially in this case. But what this really means is that in this equation, I assumed my RAX to be incorrect. And remember where this plus comes from. This plus does not come from a positive x direction. It comes from the fact that I defined everything that goes to the right to be positive. And so now, with that definition in mind, I find that my RAX is negative. And since it is negative, I actually have to flip it around. And yes, in this case, it coincides with a negative x direction, but this is not always the case. Please keep that very much in mind. So this is very important here that I have a negative here. And what that really means for my drawing is that my RAX is pointing in this direction with minus, well, now it's positive, 34.2 Newton. That is my real answer here. And please also note that in sketches you never use a negative number. So never put a negative 34.2 in the right direction. Always put a positive 34.2 in the left direction. All right, the same is true for all the other equilibrium equations. Let's go ahead and solve those. So let's, for example, find RAY, which is the sum of the moments about point B being equal to 0, counterclockwise positive, and then 0 is equal to, I always start with my unknown, which is negative because it turns clockwise in this case, minus RAY times 4 meters, that's 3 plus 1, right? Plus 20 Newton. And now about point B, so I'm taking the sum of the moments about this point, so 3 meters times 3 meters. And now I need to consider the 100 times sine 70. So 100 times sine 70. And that needs to be multiplied by 2 meters now. But let's pay close attention to the rotational sense. It rotates about this point and it's going down, and therefore it rotates clockwise, which makes this negative. So this needs to be a negative number. And let's spend some more time thinking about this, although I said it before, but I'm rotating about this point, right? So notice that this is a negative force and this is a negative force, or I should better say it points in the negative y direction. Both of them point in the negative y direction. But here my 20 has a positive sign and my 100 sine 70 has a negative sign. And so you can see here that this sign is not affected by the direction of the force, and by direction I mean the y direction. It's really dependent on the rotational sense. You can call that a rotational direction as well, but this one here turns about this point clockwise, negative, and this one turns counterclockwise, positive. So that's what you see here in this equation. And you can solve this equation now for RAY. So RAY in this case actually happens to be, believe it or not, negative 31.98 Newton. And what does the negative mean now? That means that I was wrong here as well, right? I assumed it to go up. That's what I assumed here. Up, notice that here the negative up stands for rotational direction, not for the up direction. But I find that it's negative. And the negative here tells me, Raphael, you were wrong about assuming that it's going up. You actually have to make it go down. And therefore, I have to say that 31.98 Newton in the downwards direction. And that is my true result here, right? Because I never use negative numbers in sketches as an engineer. That is a no-go. So I have that answered. And actually I have this one answered too here. So let's put that with description. And last but not least, I need to find RBY. I could use force equilibrium, but I choose to use the sum of the moments about point A being equal to 0, counterclockwise positive, and then 0 is equal to RBY, I always start with my unknown, turns counterclockwise, therefore positive, has a lever arm of 4 meters. Now I need to consider the 20, so the 20 Newton, and that is multiplied by 1 meter if we turn about point A. Yes. And then we have a rotational sense that is clockwise, therefore it's negative. And last but not least, I need the 100 sine 70, which has a lever arm of 1 plus 3 plus 2. So 1 plus 3 plus 2 meters. just to have that properly in your notes. And that is turning clockwise, therefore it's also negative. And if you solve this now, you will find that RBY turns out to be positive 145.9 Newton. And that is a result that tells me that I was right about my assumption. So the positive tells me, Raphael, you assumed correctly, and I know that my support reaction 145.9 Newton is actually going upwards. And that is my ultimate result here, which I now have to provide with an answer arrow. And that completes all three of my answers. Of course, if I were in an exam right now, I would certainly run a check. So my check here is the sum of the forces in the y direction being equal to 0, and 0 is equal to, careful now, because the first one is going down, right? So minus 31.98 plus, no, that's not true, minus 20 plus 145.9 and minus 100 sine 70. And that comes out to be minus 0.04 something, but that is equivalent to 0 in an engineering sense, and that works out. So we now solve this problem as well, and I think you have seen another variation of these support reaction problems where you may have to flip your direction of your original assumed sense. In fact, that was true here as well, so let me highlight that here as well. So we have here 31.98 going down. And that is important that you understand that and properly indicate this, so you always include this arrow and show me which direction the force is actually acting. But this completes this problem, and I think we have one more left for today, and then you're ready to solve your homework. So here the fun gets a little bit more intense, but I would say also a little bit more fun. So what we have here is a structure with different 90-degree angles that has two forces acting on it. And what makes this problem so interesting is that we have the supports at a different elevation. So this here is higher than support A, for example. And therefore, this support reaction has a lever arm about this support as well. And these problems come in really many different variations, and you're really encouraged to set up your own problems and try them, because I can even show you this one right now and you can understand it completely. But my experience in the classroom is as soon as we change something a little bit, so for example, we bring the support reaction a little bit further down, so maybe down to here, then the student might be a little bit more confused or again confused. So it's really important that you grasp the concept and study these problems. Now, I'm not going to solve this problem entirely for you. I'm just going to give you some hints here, and I want to talk about the actual support reaction. Of course, you understand that here on the left you have the roller, which means you have RAY acting in this direction, and then on the right side you have RBY, and you also have RBX in this case. You can also call them vertical or horizontal, it doesn't matter. RBY and RBX. And now, in the previous problems, you always had a choice, or you could solve one before the other or the other before the one. In this case, you really have no choice about this, and you understand that if you solve the problem, you have to start with one of these two. And I'm not going to tell you which one right now, but you will find that if you solve, for example, for the sum of the moments about this point, you have two unknowns that enter the equation. You have RBY and RBX that rotate about this point. If you rotate about this point, you only have one unknown here. Both of them can be solved depending on how you set up your equations and how you set up a system of equations, but there's an easy way and a hard way to solve this problem. And again, understand that the reason RBX has a influence on the moment about A is because you have an elevation difference between A and B, right? And that makes this problem really interesting. I will now give you the answers to these problems. So for example, RBX comes out to be, and I do this in random order, by the way, this is not how you should solve them. So 30 Newton would be the answer here. And then we have RAY, which comes out to be 26.54 Newton. And last but not least, we have RBY, which comes out to be 146.7 Newton. And I really encourage you to solve this problem and to pay close attention to how you go through it. This has many learning opportunities built into it. This is the reason why I'm not solving it for you right now. I want you to really go through those aha moments yourself and see how the knowledge applies without me showing it to you. So please go ahead, have some fun with it. And once you've done that, I'm sure you're ready to tackle your homework and to solve any support reaction problem that is for simply supported systems. I will now move on to talk about the upcoming homework, and I wish you good luck with this.